Hello YouTube. In this video I'm going to talk about this 3D Finder touch probe that I bought. I'm going to tell you more about how to mount it and how to calibrate it. I'm going to walk you through some repeatability tests that I've made, how I've done the wiring and how I interface it with Linux CNC, and also very important, how I break it and what not to do to avoid my mistake, and very important, how this got fixed. So next I'm going to walk you through how to assemble this sensor. So it consists in three parts. Here I have an adjusting ring. It's very important when you buy a sensor to be able to adjust it radially, because due to some eccentricity of the spindle to some runout, if you don't have the ability to center this, you won't be able to get precision. People in this field know that every mechanical system has its runouts, and these have to be compensated. So this here I have a collet, an elastic collet, and this shaft will get here in this collet, and once it's tight, I'm gonna tie this with a wrench. Okay, so once this gets into the spindle, you can compensate for some runout of the spindle and of the cone itself by adjusting this A screw. You see here there are two types of holes labeled as F and A. F is for fasten and A is for adjust. These are on both sides. So next I'm gonna add these screws. First, according to the instructions, you need to add the fasten screws, but not fully tight them. Basically, all you want is just to stay in place, not to fall out. Okay, so now, yeah, I got it wrong. Right now I'm showing you how not to do it. Yeah, here. Okay, so now that I got this fastened, here it has a bit of play, and that's normal yet because I haven't added these screws. So now I'm gonna add these screws, but not tie them fully, because in a few moments I'm gonna go to the machine, clamp the sensor into the spindle, and I'm gonna do the adjustment there. So these screws are just, I'm applying no torque at all. And it comes with 2mm tip, and this 2mm has a ruby ball with 3mm thread. Okay, so now using these two drills, I'm gonna use these two drills to tighten the tip in place. Okay, so now the tip is in place. So now we will be able to measure X, Y, and Z directions. One important aspect that I need to mention is the length of the probe, especially for the hobbyists who have gantry machines with low Z height. The length of the probe is 75mm, and the tip has a ruby ball, so it's a professional tip like Rennie Shaw has, and the length of the tip is 25mm. The diameter of the probe is about 40mm. Stainless steel, it has a nice rubber seal here. Swiss made 3D Finder. Actually, this Swiss made was the factor that convinced me to go with this probe, because actually I didn't know anything about it. There were no reviews about it. nothing I could find. So by this video I'm trying to help other people take an easier decision regarding this sensor. Also, one very important aspect is that the way I did this wiring is because my controller has PNP inputs. So there are two types of inputs, PNP and NPN. So if you don't want to do this wiring, you can avoid this by buying the hot plug interface. That would add an extra layer of protection to your sensor. And also, if you have other sensors that are PNP or NPN, you can just connect those sensors to that hot plug interface, and it would work with both PNP and NPN inputs from your sensors. Fortunately, this sensor can be wired both as PNP and NPN, so I just changed the wiring to be as in the schematic. For a PNP connection, you need to wire white and brown wires together, blue wire to ground, and the green wire should be the signal. So if you want to avoid all that, just buy the hot plug. It's gonna be simpler. Okay, so now I'm gonna show you how to calibrate the touch probe. One important aspect is to make sure that each time you clamp the tool, it goes into the same position. So for this I'm gonna make like a blue line here and a blue dot here. And each time I will clamp the tool, I will make sure that these two are aligned. Okay, the other aspect. So now I got the ball. I got these two balls almost close together. I'm gonna fasten the screws so that it doesn't wiggle anymore. They're not too tight, only in the adjustment screws are those that matter. Okay, and now that it's not wiggling anymore, I'm gonna jog the x-axis. I'm gonna jog until these two balls are aligned, and then I'm gonna make sure they touch each other until my dial indicator reads 0. This indicator is 1/100 of a millimeter. So without any touch, let's see what's the deviation. Very good, only 1/10 without making any kind of adjustment. Okay, and now let's start the adjustment. I'm holding the hand here so that my spindle light is a bit too bright and it blinds the camera. So I don't know if you can see on the indicator, but it's less than 100 millimeter runout. It was quite easy to adjust, but I decided not to follow the instructions and just go with my feelings that apparently were not so sharp. First I'm gonna jog in increments of 100 of a millimeter. You can see the dial indicator is at 0 and the light is green. So I'm gonna do one increment. You can see it on the watch, you can see it on the dial, not on the watch, and you can see the sensor green light has switched off. So now if I go back, green, off, green, off. Okay, now let's see if we go to smaller increments, let's say 1,000 of a millimeter, how precise it is. Okay, so at 004 gets closed. Wow. So this has 1,000 of a millimeter precision. It's just insane. but as you can see on this video, here we are also talking about the error of the machine, but I'm surprised this is so precise. I was not expecting this. So now I'm gonna do an outside measurement of this ball bearing. So here we see the measurements that we've made. The last two lines are the outside measurements, and the first three lines are the inside measurements. So the inside is 20 millimeters for the ball bearing, and the outside is 47. So you can see here it's basically missing 1/100 of a millimeter, and on the exterior it has plus 1/100 of a millimeter. And this is due to the tip offset, basically due to the accelerations of the machine and the latency on which the signal gets propagated into the controller until the controller tells the motors to stop. There is a bit of delay, and this delay can be compensated by setting the probe tip diameter. If I set this to 2 millimeter, which is the actual diameter of the ball, these values would be, I think the inside would get smaller and the outside would get larger, something like that. And if I vary the diameter, this value, one would go up, the other would go down with about the same amount. So for now I'm quite happy with the values I have. I think these values are quite dependent on the machine you have and on the controller you have. But for me, 1/100 of a millimeter, it's more than acceptable. Now I'm gonna tell you more on what and how I've managed to actually fry this probe, how I managed to break it. When I rewired the entire electrical cabinet, I kept a wire for this plug. So each time I want to remove the sensor, I just unplug this and remove the sensor. But then I thought about another problem. What if accidentally I can turn on the spindle while the tool is it's in place, and it would wrap the wire around and tear it apart? Okay, so in order to fix this, I made a hack, not kind of a hack. So here you can see we have 3 pins, and the way I'm wiring this, the way I mentioned earlier when I assembled the sensor, that I changed how the wiring it is. So in this pin over here, the one to the left, I have plus 24 volts. The one over here, it's ground. The one on top, it's a sensor presence. So basically when I'm plugging the sensor, this is gonna tell the Linux CNC controller that the sensor is plugged, and it won't allow to start the spindle. And the second, the one on the bottom in the middle, is the signal. So basically I have two signals I'm sending two signals into the controller. One of them is the cable is plugged, and the other one is probe is tripped. And when I'm reading this into Linux CNC, basically I'm doing an AND between these two. So I'm saying if sensor is plugged and probe is tripped, then consider the signal and send it to motion input. Why I have to do an AND? Because the signal is negated, because the circuit is normal closed. So how did I burn the sensor? So the thing is that while testing this routine with plugging and unplugging the sensor, I wanted to see what happens if the spindle is on and I plug the sensor. Of course, the tool was removed from the spindle, And I plugged and unplugged this a few times. But then I made the fatal error. With this plugged in, I pressed this button. And that was the fatal error. Because that button is linked to a solenoid. A solenoid is basically a coil. Has a coil inside. And that coil is an inductor. So the problem with that is that when I press the button and the sensor was plugged, when I release the button, there was a voltage accumulated in that coil, and that caused a spike. And in generally, these kind of spikes are kilovolts. So this fried my sensor. I didn't know what to do, and I did what most hacker and maker would do. I opened it to see what's inside, what got broken. Initially I had no idea why it broke. Compared to the traditional, compared to what you will see on YouTube with basically two rods and a ball that sits between two rods, or one rod that sits between two balls, it's a different approach. Basically here it's a cone, it's a ball that sits in a cone, and that's more precise, and the cone are gold plated and the balls also are gold plated. I measured them with a 1000 division micrometer, and they're damn zero. There is perfect zero. Okay, so I ended up debugging that sensor, and I found out that there was a chip, an ADG, I can't remember the serial number, an ADG chip that got fried, and I couldn't find that chip. It's used in aviation, so I cannot buy it by myself. You need to be a special, I don't know, company with a special profile in order to be able to buy that kind of product. So after doing some debugging, I wrote Sorotech. I didn't do what I took the wrong path. I should not have opened the sensor first. So I was expecting them to dismiss me, but fortunately they didn't. To my surprise, someone from Sorotech, someone from the company, Sorotech forwarded me to the company that was building this sensor, and I had the best customer support ever. This is all I can say. A technical guy answered me, and I explained what I did, what I tested, and he came back with numbers, with what to test, with what measurement to make, and he basically helped me debug this. After a few tests, he concluded that yes, the ADG is fried, and he couldn't explain how this happened, because it has so many protections on it, and it's an avionics chip. That's why it's so, I think it's expensive. So he asked me to. We talked a bit on the phone. He was very helpful. He knows a lot about this sensor. We agreed to send him the board for diagnostics, so that he can investigate himself, and he'll send me back a replacement board. So he sent me back a replacement board. I mounted the board. Everything got perfect, and basically the sensor and the measurement that you saw now are containing the new board. So right out of the box, everything was fine. I cannot be grateful enough for the customer experience I had. I was expecting, this is it, I threw almost 400 euros and that's it. But this could have been avoided. In order to avoid this, if you mount a flyback diode in the solenoid, you can avoid this. And at that point I didn't know, but due to discussions with him, we realized together that that's the issue, and he told me he faced a similar issue on one of his older machines where something was going nuts and he didn't know why, only when some relays were actioned, and basically the relays have solenoids inside. they have coils inside, so they act like a solenoid. So while talking with him, I was able to isolate the issue and spot the issue and basically got the issue fixed. So right now I installed flyback diodes on the relay, and just as a safety measure, I'm never pressing the release cone from the spindle while the sensor is plugged in. I don't want to risk it again. So this is my review for this sensor. I really love it. I hope others will find this useful. When I bought this, initially I didn't know where to start from. I searched for a bit. I looked for Renishaw and for rather more expensive, but paying 1,000 euro for a second-hand Renishaw was not an option for me. It was too expensive. Also, Drutronics seems promising, but $700 plus shipping plus customs, being in Europe, I don't know, it's not such a good deal. I mean, I think this sensor is a good deal even for the guys that are in America, and they will have to pay customs or so, because they would go cheaper than the Drutronics. I don't have experience with Drutronics. I'm not trying to discredit them, but this is just my honest review on this.